Okay, and then one of the whole points of knowing electron configuration is because it leads into this concept of periodic trends. I am actually going to break this into two movies because it is a little bit long, and I want to make sure I get through all of it and not make it forever long. So these are all the periodic trends I'm going to talk about. I'm going to talk about these 5 first, and then I'll move into these 2 because those are the 2 hardest, I think. So the periodic table was originally organized by a guy named Mendeleev. He originally lined it up in terms of atomic masses, and it worked pretty well. Potassium and argon are off a little bit. There's a few others that are off a little bit. But once they figured out how many protons and things like that are in each element, then they lined them up according to atomic number. And the way he set it up is he had elements in the same column have similar properties. For example, in the first column, you have the alkali metals. They all react very vigorously with water. They all get a positive 1 ionization. They're all shiny. They're all metals. They're all soft. Variety of different things. So the reason we know elements in the same column have similar properties is because they have the similar number of valence electrons. And the periodic trends depend on 2 things: how many protons there are in the nucleus and the arrangement and the distance of the electrons in the orbitals around the nucleus. So that's what this is electron configuration, and this is atomic number. It's really pretty much those things that determine the periodic properties. So the first one we're going to talk about is valence electrons. They are electrons in the outermost principal quantum level of an atom. That means the ones that have the highest N value. Basically, it means the S and P electrons in the highest energy level. Okay, so you need to look back at your electron configurations for these. If you look at magnesium, it was neon 3s2. It has 2 valence electrons. If you look at manganese, it ends in argon 4s2 3d5. It has 2 valence electrons. Iridium is, I forgot what it was, is xenon 6s2 4f14 5d7. It has 2 valence electrons. Arsenic, on the other hand, was argon 4s2 3d10 4p3. So S and P electrons added together is 5. And iodine with 1 minus was argon, krypton, 5s2, 4d10, 5p6. 2 plus 6 is 8. That's the most you'll ever see is 8 valence electrons because that fills the S and the P's. Okay, atomic radius is tied to a couple of things. So trying to figure out how big an atom is, and that's literally what this is. It's hard to know because we don't know exactly where the electrons are. So we're just going to kind of estimate it at 90% for them. And this is probably, of all the things in AP chemistry, the single most important law governing a lot of things. It's something called Coulomb's law. It states the force between 2 charges is proportional to the amount of charge on both charges and inversely proportional to the square of the distance between them. But it's an attractive force. Okay, the attractive force between 2 things that have a charge. That's the important thing to recognize. Between protons, electrons, if we were talking ions, anything that has some kind of an attractive force because of opposite charge, it increases when there are increasing charge. So the effective nuclear charge is greater. That means the positive charge in the nucleus, since we're talking about protons and electrons, and if they get closer together. So the distance between them is smaller, the protons and the electrons are closer together, the attractive force is stronger. So this deals with atomic radius, but when we talk about ions later, it's the same idea. So here's the trends in atomic size. Atomic size gets smaller as you go left to right within a period, and it gets bigger top to bottom within a family. Okay, that's the general trend. Whether you memorize that or not, that's up to you. But what I'm never going to ask you to explain why it increases from top to bottom within a family and expect you to say it's because that's the trend. Okay, I want you to understand why. So it increases from top to bottom within a family because the number of energy levels increase and the electrons are increasingly farther away from the protons in the nucleus because of those energy levels, and they're not allowed to move between energy levels downwards because they're full. So it's based entirely on that. So lithium is 1s2, 2s1. There's the protons, level 1, level 2, that's the radius. Cesium is xenon, 6s1. So there's protons, 1, 2, 3, 4, 5, and 6. There's the electron, and that's why its radius is bigger. Even though it has more protons pulling on that charge, it's got 55 protons versus 3. The fact that those energy levels are blocking this outside electron, and it can't drop down, it can't go in the middle, it's not allowed, its radius is huge. Okay. The other thing is the shielding effect. The increase in the number of energy levels shields the electrons in the highest energy level from the attraction of the protons in the nucleus. This is where we're going to talk about something called core electrons. Okay, here we have 2 core electrons in this level. Here we have 54 core electrons. And so what you have is bouncing around in here is 54 negatives moving around so that those 55 positives can hardly attract that outside electron. Here, I have 2 electrons moving around. And those 3 protons pulling on that 1 electron, it's not huge. Okay? So, the atomic radius decreases from left to right across the period because you have an increasing positive charge and the electrons are all in the same energy level. So if I was to compare lithium and neon, I have 3 protons, 1, 2, it's 1s2, 2s1. This is 1s2, 2s2, 2p6. I have 10 protons in the nucleus, energy level 2. Okay? Because my core electrons are the same, they both have 2 core electrons. The effective nuclear charge here is 10 protons minus the 2 electrons in the core. That's an effective nuclear charge of 8. This is 3 minus 2. This is an effective nuclear charge of 1. That increased effective nuclear charge pulls those electrons in closer, and the radius gets smaller. It's the net positive charge experienced by each valence electron. So, number of protons minus the core electrons, and I did that up there. Okay. So, explain why the atomic radius of iodine is greater than fluorine. Don't tell me iodine's closer to the bottom. Fluorine has 9 protons. It's 1s2, 2s2, 2p5. Iodine has 53 protons, and it is krypton, 5s2, oh goodness gracious, 5s2, 4d10, 5p5. So I have 2 energy levels, 5 energy levels. Increased energy levels plus in iodine plus increased shielding effect of 36 electrons, core electrons, increases the radius in iodine. Okay. Explain why the atomic radius of krypton is smaller than calcium, even though it has more protons and electrons. So calcium is argon, 4s2. Krypton is argon, 4s2, 3d10, 4p6. So they both have 4 energy levels. But argon and krypton have different numbers of, this has 20 protons, this has 36 protons. So the increased number of protons in krypton pull the electrons let's be real clear, valence electrons closer. If you wanted to talk about effective nuclear charge, this is the core. I have 20 minus 18. I have 2 for an effective charge. Here I have 36 minus 18. I have 18 for an effective nuclear charge. Okay, reactivity. Metals become more stable by losing valence electrons and becoming positively charged ions. Increasing reactivity goes along with increasing atomic radius because it's easier to lose an electron that's further away from the nucleus. It's not held as tightly. So metal reactivity increases down a column because of atomic radius increase, and it decreases across a period because the atomic radius decreases. It's harder to lose those electrons when they are closer to the nucleus. I've got a couple of videos if you feel like watching them. Okay, nonmetals are the reverse. They tend to become more stable by attracting enough electrons. So they're going to pull more electrons into them to fill up their valence orbitals, and they become negatively charged ions. That means the increasing reactivity of nonmetals depends on the radius being small and the ability of the electrons to attract them, as well as the stability of the energy level. It decreases down a column because the radius gets bigger. And it increases left to right across the row, but again, only from the nonmetals section. Okay? Common ionic charge depends on whether the element's a metal or a nonmetal. Valence electrons, remember those are the S and P electrons, are lost or gained in order to fill or empty the principal quantum number. Metals generally lose all their valence electrons and get a positive charge. Nonmetals fill their valence electrons, so they fill up the S and P completely and they get a negative charge. So predict the most common charge. Basically, first thing you want to do is identify the metal or nonmetal. So this is a nonmetal, nonmetal, metal, nonmetal, metal, 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 nonmetal. So first thing I would do is, if it's a nonmetal, I'm going to write negative, 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 and negative. Metals are positive, 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 positive. Okay, so the valence electrons. Tellurium is 5s2, 5p4, so it has 6. Krypton is 5s2, 5p6. It has 8. Magnesium is 3s2. This is a nonmetal. I'm going to add those together. My S and P is 5. It's 2. This is a metal. I'm only looking at the S's and the P's. That's only 2. Copper, if you remember right, is 4s1. It's only got 1. Metals, 2 plus 1 is 3. Nonmetals is 6. Okay, and then if it's a metal, I'm just going to take this number and make it positive. Positive 2, positive 2, positive 1, positive 3. If it's a nonmetal, I need to fill it up to 8. Negative 2, up to 8, negative 3. It is at 8, so 0, so negative doesn't really apply. Up to 8, negative 2. And that's how you do it. Okay, electronegativity, I'm not really going to get into too much here. It's more in the next chapter. It's similar to the idea of ionic charge. It's the ability of an atom to attract electrons to itself. But here's the big thing. In a bond, when two atoms come together and form a molecule or a compound or something like that, it's the ability of the atom in that bond to attract the electrons to itself. We're going to deal with more of that in the next chapter when we talk about bonding. So atoms with a high electronegativity exhibit nearly full orbitals. Taking on an extra electron results in filling the sublevels and increasing the ability, stability, and lowering its energy. That means they want electrons. They're very strong attractive forces. Atoms with low electronegativity exhibit orbitals that are not close to being filled. Taking on an extra electron doesn't result in filling the sublevels, and it doesn't increase the atom's stability, so they tend not to take them on. It's actually easier for things with low electronegativity. It's more stable for them to lose those electrons and get a filled orbital. And bonds form between atoms when an atom that has higher electronegativity is able to take or share electrons from an atom with lower electronegativity. So I'm going to give you a chart, but we'll talk more about it in Chapter 8. What's going on with all that? All right. So if you notice in here, the electronegativity and the atomic number, if you notice, electronegativity increases going across the row, but there is nothing available for neon at all. And sodium increases going across the row. And again, there's nothing for argon. Neither one of those are available. Now, when you're doing the starting with potassium, you have the transition metals, and so they're kind of in here. But again, it increases. But here's krypton. That means it must be possible for krypton to form compounds. Now, it's only going to form compounds if something else is higher up on the chart. So like Cl or F or O maybe, or N maybe. But it's only going to form compounds if it's something that's higher on the chart that can pull away its electrons. Neon and argon aren't even listed because there are no compounds with neon and argon. They hang on very tightly to their electrons, and they don't share them with anybody. And they certainly don't want any more. So they're never going to form compounds. But if you notice xenons over here too, it's possible for xenon to form compounds, primarily because those two have a very large atomic radius. Okay, I'm going to stop